Okay, so now let's talk about adaptive Runge-Kutta method. So till now, if you see, the problem that we solved had a constant step size. The step size that we took was all constant, like 0.5, 0.3 and so on. Okay, but in real life, if you want to solve really complicated problem, you have to use adaptive Runge-Kutta method. Okay, so basically in adaptive Runge-Kutta method, what we do is we don't keep the step size constant. We change it or we adapt it depending on the situation. So the question here might be, in which situation will adaptive Runge-Kutta methods, sorry, since we'll be talking about two methods, so it's methods. Anyways, let us come back to this. So the question that might come in your mind is, in which situations actually you encounter or you use adaptive Runge-Kutta methods. Okay. So till now, if you see the problem which I was solving, the solution of the problem was pretty simple. Okay, like this, like the previous problem, I think solution was something like this. It was a very good looking solution. Okay, but sometimes if you see, if you get this kind of problem where there is a jump, okay, and this jump is not constant, it's a drastic jump. You know what, when it's short duration time, if you see, it's going from a positive value to a negative value. I can again, let us say like this. So within a short span of time, if you see, it's going from a very high value to a very small value. Okay. So if you want to capture this kind of solution properly, you'll have to use adaptive Runge-Kutta methods. So basically what we do here is, when you are on this part of the problem, you use, because if you see, this is just a continuous curve. So when you're on this part of the problem, you use constant step size, or a step size, rather than saying constant, I can say you are going to use a step size which is very high, the value of which is very high. But when you come here, you cannot use high step size, because if you use high step size, that high step size is not going to capture this sudden jump in the magnitude. Okay, so what we do here is we use a very small step size. Okay, and then for the rest of the problem you use a coarse or a high step size. Okay, so this is how your adaptive Runge-Kutta method works, or adaptive time stepping as well. This is also known as adaptive time stepping. Oh, sorry, a step adaptive step sizing, time stepping, adaptive step sizing. So you have to change the size of your steps when you reach this kind of problem where there is a sudden jump, okay, or discontinuity maybe. So how you are going to solve this kind of problem? So when you talk about adaptive Runge-Kutta methods, the first method that we are going to discuss is, we are going to discuss step halving. Okay, so what you do in step halving is, basically, if you have a step size, let us say h, okay, so what you do is, first you solve the problem considering the step size and you find out the value. So what you do in step halving is, you solve the problem in two steps. First you are going to consider the step size h. Considering step size h, you are going to solve the problem and find out the value of, you are going to find out the solution. In the next step, what you are going to do is, you are going to reduce the step size. Okay, when you say reduce the step size, you are going to reduce it by half. Okay, so first you are going to take h by 2 and then you're going to find out the value of let's say y, okay, or ya. You're going to find out the value y1, and then again for the second step you're going to again find out the value y2, and then your yb is going to be y1 plus y2, and that is going to be your second value of y. So first you consider the step size, full step size, and then for the second part you consider half of step size. Okay, so once you find out these values, what you find out is the error. The error is nothing but delta. Okay, and this error is known as your present error. So this is known as your step halving. Now what you are going to do after calculating this error, I'll show it to you once I discuss another method. So this is your step halving. Okay, the problem with step halving here is basically, if you see, you are doing same calculation. Like if you were solving this by Runge-Kutta method, okay, you'll have to calculate k1, k2, k3 and k4 for this, and again when you are solving k1 for this, k1, k2, k3, k4 for this, again k1, k2, k3, k4 for this. Okay, so if you see how many times you are calculating k1, k2, k3, you are calculating 3 times. Okay, so because of this, the computational complexity of step halving increases. To circumvent that, what we are going to discuss is known as Runge-Kutta method. Okay, so what does Runge-Kutta method does is, the idea behind it is very simple. So whatever disadvantage, if you see, okay, so what Runge-Kutta method does is, it uses two equations. Okay, this is going to be your first equation, and this is going to be your second equation. So what it does is, it calculates the value of y by using first the fourth order method, then using fifth order method. Now if you see here, we were calculating k1, k2, k3 again and again, but in Runge-Kutta method you just have to calculate k1 once, k2 once, k3 once, k4, k5 and k6 once, and you just have to use this k1, k2, k3 here. So this reduces the computational cost, okay, and number of function evaluation. So if you see how many function evaluation you're doing here, 1, 2, 3, 4, 5, 6, 7 function evaluation. But if you see here, you're doing 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so number of function evaluation, if you see here, is more and here is less. This reduces the computational complexity. So again, what we do is, we use this and we calculate the value of delta. So delta is going to be what? Y using the fifth order, that is this. Let me call this as B and this is A. So delta is going to be YB minus YA or YA minus YB, whatever. Okay. So now the question is, after calculating this delta, what actually we do? So now what we'll be discussing is what we'll do after calculating the value of that delta. So this is known as step size control. So to control the step size, what we are going to do is, you are going to use this formula, that is H new, that is new step size, is equal to H present, that is present step size. Okay, that is delta new, and this is going to be delta present, raised to alpha. Okay, so from where you are going to find out delta present, you are going to find out delta present from here, using step halving, and if you use Runge-Kutta fallback method, you are going to find out from here. So once you find out delta present, you can calculate the new step size. Now what about this alpha? Okay, so we'll define alpha. So basically this is the equation where alpha is 0.2 when delta present is less than equal to delta nu, and alpha is equal to 0.25 and it is equal to 0.25 when delta present is greater than delta nu. And basically the delta nu is what we are going to decide how much precision we want. So delta nu is equal to eta, where eta is known as tolerance. We'll decide into y scaled. Okay, so this is something we can define by ourselves by considering the nature of the problem, and then where y scale is this. So this is how you're going to find out the new step size. Again, if I repeat, so what we do in adaptive step size when it is required on this kind of problems. Okay, and when you talk about methods, there are two methods: step halving and Runge-Kutta fallback. Step halving, what you do is, the problem is you do a lot of function evaluations, that is why it is computationally expensive. But Runge-Kutta fallback, it's computationally not expensive. You just have to do function evaluation k1, k2, k3 once, and you can find out the value of delta present. So once you find out delta present, delta nu is something that we are going to define, and we can find out the new step size that is required. Okay, and the value of alpha is based on this. Okay, so if you want to increase or decrease, will based on your delta nu and delta present. So this is your adaptive Runge-Kutta method.